Hello, chemists. I'm going to continue our conversation about bonding. We are going to focus on covalent bonds because covalent bonds are very important in biology and nutrition. We're going to mention ionic bonds and we'll talk about those a little bit later in the quarter. So just jumping right in, making sure we're looking at those objectives, covalent compounds, drawing Lewis structure for covalent compounds, naming them if they have two elements in them, predicting the shape around the atoms in a molecule. We're going to talk about something called electronegativity and the polarity, which is really important in solubility. We spoke about water dissolving things versus bile or oil-based things dissolving in a polar substance. And then we'll talk about the polarity of a molecule itself. Okay, so we're going to jump right in and just begin to talk about what does it mean for a substance to bond together. So a chemical bond, all right, a chemical bond has, for our purposes, two flavors, right? There is an ionic bond, and those are, our favorite ionic substance is sodium chloride. It is a metal connected to a non-metal, and the process of that is to achieve that octet we spoke about before, that octet, that stability, that atoms are looking for when they bond. And what happens is the metal actually transfers its electron to the nonmetal. So this involves an electron transfer, and that's from the metal to the nonmetal. Okay, and we will talk about those a little bit later. We're not going to focus on that to start with. Okay, second type of bond and more important type of bond is a covalent bond. Okay, so covalent bonds are the bonds that exist between all the macronutrients. They exist in all your DNA. They are really the bonds that are important to life, essentially. Okay. And essentially, a covalent bond is also an attempt to achieve the octet and stability, but they just do it in a different way. It is going to be between two nonmetals, two or more nonmetals, okay? And rather than electrons being transferred, it is sharing of electrons. So electrons are shared, and again, both of these substances, in order to make this chemical bond, are trying to achieve this stability and this octet. So, but they just do it in different ways. Metals transfer the electron to the nonmetal, so they both get an octet. Covalent bonds to nonmetals, the electrons are shared in order to achieve that octet. In most cases, there are some examples. Okay, so that kind of answers this question here: ionic bonds and covalent bonds. And we also call covalent bonds molecular bonds. Okay, so I'm going to focus just a moment on ions. And just kind of go there for a second. We'll talk again more about this later. Ions are different from atoms. And again, this is going to go back to our protons and electrons. Atoms are neutral. Okay, and that's because the number of protons are equal to the number of electrons. So if we think about that example of sodium that we talked about before, we know it has 11 protons because its atomic number is 11, and we also knew that it had 11 electrons, which makes it neutral because these positive charges and these negative charges cancel each other out. So a sodium atom is neutral, okay? A sodium ion, all right, and the symbol for that down here is we're going to put the element symbol, and we're going to put its charge up here as a superscript, okay? So for this case, I have sodium, it's a +1 charge. It still has 11 protons because if it didn't, it wouldn't be sodium. But it's lost an electron, and that's because it wanted to achieve stability by doing so, and it gave it away to something else. And so when you take this 11 positive charges and add it to 10 negative charges, you're going to get this +1 ion. And so we're symbolizing that ion with this charge right here. Sometimes you'll see it as a 1. Most of the time you'll just see it as a plus. Okay, ions come in two flavors. They are charged particles, basically. Okay, so they are charged particles. All right, And they do this, they get charged by losing or gaining electrons. Okay, and so when we think about a cation, which is positive, okay, these are positive, and you can remember that if you remember that cats have paws. Okay, calcium 2 plus is a cation, sodium plus 1 is a cation, and all metals tend to be cations because they give away electrons. So there's a loss of electrons here. And again, they're trying to achieve stability. Anions then are negative ions. They are negative ions. Okay, they are the nonmetals. And those gain electrons. And again, they're doing that to achieve stability. So again, we'll talk about this later. I'm just going to give you a quick visual on this. We'll give you this chart so you have it. And what you can see here is that when you look at this periodic table, different than the last, basically, if I cut these in half and I talk about my metals over here, right, and my non-metals over here, you can see that there's that chlorine ion we just spoke about. Everybody over here adds electrons, gains electrons, and their attempt is to get like a noble gas. That's how they achieve their stability. That's how they achieve their octet. Of course, there is the exception. Hydrogen only wants one more electron to get like helium. These guys over here all lose electrons, and that's because they go back to the noble gas behind them. They are achieving an octet. They're doing it by loss of electrons rather than gain. So we can see that in the periodic table. Okay, we're going to put ions down for a bit, okay, and we will come back to them later. Just wanted you to kind of have that rudimentary knowledge. We're going to move into covalent compounds, okay? And when we talk about covalent compounds, I just want to start with some basics, just how we name them. And when we name covalent compounds, it can be very complicated unless they're just two elements. And I'm just going to kind of bring up two that I'm sure that you know of, okay? This is carbon monoxide, okay? And this is carbon dioxide. And the way we want to speak about this is we know that this is a combination of carbon with oxygen. Okay, you'll notice when I write the name, I remove the suffix and I put in the IDE. So this is what we call a suffix. So that is one of the things that we do to change it. So the second substance gets its suffix changed. The first substance, you'll notice, doesn't, okay? And then we use a prefix, okay? We use a prefix right there to give you the number. And what's interesting about this is when covalent compounds come together, they can come together in multiple ratios, and we have to make sure that we tell you that ratio so it's really clear. So this one says I have 1 oxygen, right? And this one says I have 2 oxygens. And there's those subscripts, again, that tell us that, okay? There is some practice on this, and I have already done the answers for you. So I'm going to go here. Where are those questions? Right here. So basically giving you some practice on writing those names. So I have that figured out for you, so you get to practice that, okay? So basically just naming covalent compounds. Again, it gets a lot complicated when there's more than 2 types of elements, but I'll just kind of leave this for you to look at. The prefixes that you might use are here, monodi, you're familiar probably with these, and these are the prefixes you'll know. I just spelled carbon wrong. You'll notice that we don't have a prefix here. You can put mono on here if you wanted to, but it's just redundant. And an example of maybe something you've talked about in another chemistry class, we have a common name for water, but we could call water dihydrogen, okay, monoxide. That would be how we might name water using these rules, right? The di for the 2, the mono for the 1, dihydrogen monoxide might be a way to name that. You could just as well call it dihydrogen oxide because the mono is optional. Okay, just some information that I have to convey. I'm going to basically talk to you a little bit about the fact that there are 7 particles, substances that don't like to be by themselves. We call them diatomic. And the reason I'm throwing it in here is because they are covalently bound together, and they are substances you're very familiar with, covalently bound. Okay, and that's why I'm just throwing it in here. There's no other good place. There are 7 7 substances that are diatomic, and it's really easy to see them on the periodic table, so I'm going to show them to you first. Basically, iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen do not like to hang out by themselves, okay? There's no other good place to tell you this. I'm just going to tell it to you so that you know. We call these elemental. When you ever see the word elemental, we're talking about these elements that are just elements. We talked about elements versus compounds earlier. And I actually threw these in iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. So there are 7, right? 1, 2, 3, 4, 5, 6, 7 diatomic molecules. And these are elements that hang out together. There's a mnemonic to remember this. I don't know if this helps, but it might. I bring clay for our new house. So each of those, I, BR, CL, FO, and H, help you remember that. You can also see it on the periodic table. I have had other students tell me a different way to do this, and I'll just share it with you. It is have no fear of ice cold beer. It kind of works. Whichever works for you is fine. And I'm just going to leave it at that. But that's something you just need to know. Okay. I'll tell you why and where you've seen this before. We talked about decomposition, and we didn't explain like why when I wrote this decomposition reaction we had H2 and O2, and that's because those guys are the diatomic gases of oxygen and hydrogen. So when they are by themselves, we call them elemental. You'll notice that that oxygen doesn't have a 2, but that's because it's bound to something else. It's only when they're by themselves that we get these diatomics, and we have to remember that they have a subscript of 2. Okay, quick review. Basically, the number of bonds, the valence electron helps us determine the number of bonds. I'm going to sort of put this in here real quick. Carbon, oxygen, nitrogen, those are the biggies. I'm going to put fluorine in here just for fun, and hydrogen. How do we know how many bonds they make? Well, we have to look at their valence electrons. Again, you can tell those by which family or group they're on the periodic table, right? So when we look at carbon, it's in group number 4, and you can just count across 1, 2, 3, 4, 5, 6, 7, and 8. So hydrogen has 1, carbon has 4, nitrogen has 5, oxygen 6, and fluorine has 7, right? So carbon has 4 valence electrons, oxygen has 6. We talked about how to fill this in earlier in another video. Hopefully you watched that one. Fluorine has 7, and hydrogen has 1. So we asked the question, how many bonds do they make? And last time we said we take 8 minus the number of valence electrons, and that tells us the number of bonds. So again, just reviewing that, we know that carbon can make 4, oxygen makes 2, nitrogen makes 3, fluorine makes 1, and hydrogen makes 1. That's weird. It's an exception to the octet rule because it only needs 2 electrons to be stable. So that's a weird one, but that's how that works. Okay. To add to that conversation and to get us ready for the next concept, I want to talk about something called non-bonding electrons or lone pairs. So as you look at these elements right here, you'll notice that carbon, we spoke earlier that 2 electrons equal a chemical bond, right? A covalent bond when they share them, all right? So you'll notice that carbon has no non-bonding electrons. Every electron that carbon has is going to get another electron with it to make a bond. So this one has no lone pairs or no non-bonding electrons, and it makes 4 bonds, right? Oxygen, however, has 2 sets of non-bonding electrons. They're out there. We call them lone pairs or non-bonding electrons. So we could say oxygen has 4 non-bonding electrons or 2 lone pairs, depending on how you like to look at it. Nitrogen, when we look about nitrogen, it has 2 non-bonding electrons or 1 lone pair, right? When you look at fluorine, 1, 2, 3, fluorine has 6 non-bonding electrons or 3 lone pairs, and hydrogen has 0, none, right? As carbon, no lone pairs. Now, why do we care about that? It's going to be super important when we start talking about the shape around an atom. The lone pairs are going to matter when we speak about shape, okay? And that's what's coming next. We're going to start to create molecules. We're going to start to put things together, and then we're going to start talking about how they are arranged in 3-dimensional space, I guess I should say. Okay, thank you so much for listening. Have a great day.